Thank you, Tom, for the opportunity to speak this evening. It is a privilege to speak to all of you. My topic is about curriculum, so I'd like to start right in with the math problem that I find very interesting. This problem is interesting because after you've read the first two words, you pretty much know what the problem is about. And the problem is interesting because a problem like this is in basically every algebra textbook currently. The problem is interesting because it was in every algebra textbook when we were in high school, and for some of us that's a long time ago. But I didn't choose it for any of those reasons. I chose it because it's in this textbook, written in 1892, 119 years ago. Interestingly, it was written by Matthew McCurdy from Phillips Academy, Andover. Yeah, they're still using that, that's right. So the question is, what was the U.S. math curriculum like in 1892? And I'd like to offer three historical documents to give you an idea what that was like. So first, I'd like to show you pages from the McCurdy text. Numerical substitution, subtraction of polynomials, multiplication, expanding, squaring, similar, dividing, long division of polynomials, factoring, sum and difference of like powers, reduction to lowest terms, adding and subtracting fractions, multiplying and dividing fractions with polynomials, solving equations with fractions, solving literal equations, simultaneous equations, those are linear ones, the binomial theorem, exponents, negative and fractional exponents, radicals, solving equations with radicals, like number 5, a double radical, solving quadratics where binomials are embedded, systems of nonlinear equations, here's the conics, inequalities and systems of inequalities, variation, indirect, direct variation, arithmetic series, geometric series and sequences, permutations and combinations. The word problems are spread throughout the textbooks, but I've gathered them together on the following three screens. They look awfully familiar to me. Upstream, downstream. These two involve geometry. There were lots of problems involving money regularly in those textbooks. This is joint variation here. How many different permutations can be formed from the letters of Mississippi? That's currently in the Earl Swerkowski pre-calculus book. Currently. Democrats and Republicans, they didn't get along then. So that gives you a glimpse of what the curriculum was like in 1892. But I want to give you another perspective, because that's just one textbook. The College Board started in 1901, and for the first 25 years they offered only achievement tests. The aptitude test started in 1926. These are some screenshots from the early tests. There were three tests offered, sort of, if you will, level 1, level 2, and level 3. So this will give you an idea. 2 hours, just 7 questions. Two minus x, x minus 2, right? Factoring out the minus 1. Systems of nonlinear equations. So that's the easiest of the 3 tests. This is the second test. 8 to the negative 2/3. Here's the third test. There's one question that I find quite interesting. They did graph equations. Look at this 4a. Plot the equation xy equals 4 and 2x minus 3y equals 5, and on the same axes, and from the figure, estimate the solutions of the equations. Actually, quite a progressive question, I think, for 1892. This is actually happens to be 1916. So that gives you an idea, a second glimpse of what the curriculum was like at that time. The third document that I'd like to show, coincidentally, also comes from 1892, exactly 119 years ago. This is about the first standards movement in the United States. Education in the late 1800s, for the most part, followed the European model for secondary education. That included that in the 10th grade, you would make a choice. That system of education that I'm about to describe is used still for most of the European system, and actually in most of the world for secondary education. In the 10th grade, often there's a choice whether you're going to go more vo-tech or towards university bound. Students study to the 13th grade, not the 12th grade typically. Students often are studying 10, 11, or even 12 subjects at the same time, typically studying biology and chemistry and physics every year, and often studying 2 different math classes every year, let's say geometry and algebra at the same time. So in 1892, the National Education Association formed the Committee of 10, and this is the list of the Committee of 10. The president was Charles Eliot, chairman was Charles Eliot, the president of Harvard at the time. These 10 men, all men, were from universities, presidents of universities, principals of private schools, and only one was a principal of a public school. And so they made the following recommendations. And this is where we mostly deviated, and the United States became different than the rest of the world in some of our nuances. That 8 years of elementary and then 4 years of high school. To reduce the number of subjects to just 5, less is more. I'm not saying these are good or bad, I'm just saying this is where our educational system came from. They said biology in the 9th grade, chemistry in the 11th grade, and physics in the 12th grade. That's what they said. And here are some screenshots from the original document. That the study of chemistry should precede that of physics, that the study of physics should be pursued the last year of high school. Right? We have a physics first movement in the United States. It took about 110 years in order to change what the Committee of 10 arbitrarily said at that time, that both physics and chemistry should be required for admission to college. And have you ever wondered why it is that we study algebra in the 9th grade, take a timeout, do geometry, and then go back to algebra 2? Because 119 years ago, 10 men said that's what we should do. The conference believed that the study of demonstrative geometry should come at the end of the first year's study of algebra, and that's why we do this. And that all students should take college prep. So that gives you a glimpse of what the curriculum was like in 1892, and it's strikingly similar in mathematics to the curriculum that we have today. It doesn't necessarily mean that it's an inappropriate curriculum, but it does mean that it doesn't take into account anything that's happened, or very much at least, in the last 119 years. But a lot, in fact, has happened since the Committee of 10 in 1892. For instance, the population has grown from 1.5 million to 7 million. That's had huge implications for us as people. Since then, we've had mass transportation, mass communication. Medicine is drastically different. In 1951 came the first credit card. The way we purchase is drastically different. In 1955, oil overtook coal as the world's #1 energy resource. A drastic change for us. And if you consider then through the last half of the 20th century computers and then culminating in about 1990 with the World Wide Web, drastic changes for us. Going back 1 year, the standards in 1989, the NCTM standards, I think was an attempt to try to say, hey, maybe it's time to make some changes. But if you look at the summary of changes in content and emphasis, you'll see that there are bullet points specifically saying what should happen for algebra, specifically what should happen for geometry, for trigonometry, for functions, and then here at the end, just 3 words. Statistics, probability, and discrete mathematics. And what I'd like to do for most of the rest of the talk is turn this on its head. Before I do that, I'd like to say, so how's it going for us, sticking with this curriculum relatively unchanged for 119 years? First, what I'd like to do is just talk about high school dropouts. In the United States, 25% of teenagers don't graduate from high school. 7,000 students per day drop out of high school. 1.3 million U.S. high school dropouts per year. Dropout factories, sure, we lose some, but who's counting? Well, some people are counting 1.3 million. The second thing I'd like to look at is what's called math dropouts. I don't think I'm going out on a limb here saying that the traditional curriculum in the United States is designed to prepare students to take calculus. Pre-algebra, geometry, pre-algebra, algebra 1, algebra 2, pre-calculus is just really 4 years of pre-calculus. So I've been interested for quite some while and looked up the numbers to say, well, what percentage of kids take calculus and pass it? So here are the numbers that I came up with, many of these numbers, not all, came from this article. About 14% of graduating seniors had taken some course called calculus. Now remember that only we're only reaching 3/4 because 25% of the population doesn't even graduate from high school, so that's only about 10.6% of high school age students take calculus. Half of them took the AP calculus exam. So half of the 10.6 is about 5.5% of high school age students take an AP exam. Good number, 83% of them earned a 3 or higher on the AP exam, which most of us would say that's showing success in calculus. So 83% of that 5.5% is 4.6% of high school age students pass calculus. Only 4.6%. Now 6.1% of high school graduates take calculus in college, but 40% fail. So we have 60% of the 6.1 or 3.6% of college students pass calculus, and if you add those numbers together, this from high school and this from college, and actually there's overlap, there's a lot of overlap, I couldn't find those numbers, then you have approximately 8.2%. 8.2% of the population passes calculus. Our goal in our curriculum is designed to prepare kids for calculus, and 8.2% of the population at some time in their life passes calculus. Now some of you are saying, Niels, your numbers are off. I saw that one number, and I'm not so sure about that, right? Double it. That's fine. Triple it. It's okay with me. If you triple it and I'm off by that far, and I really don't think I am, then only 25% of the population would pass calculus, and in any kind of grading system, that's failing. So what does society have to say? Michael Leunig says the role of the cartoonist, as well as making us laugh at our shared predicament, is to discover and express what is repressed and to say out loud what people everywhere are whispering. So what are people everywhere whispering? We put these cartoons on our math tests, but excuse me, I don't find them funny. Tell us in layman's terms what your breakthrough means, and he can't do that. Society is telling us that mathematics is unintelligible. I had my doctor do a DNA test, blood analysis, and as I suspected, it's missing the math gene. It's saying that we're too dumb to do mathematics. Algebra class will be important to you later in life because there's going to be a test 6 weeks from now. That the reason why we're studying it is simply to do better on the next test. not because we're ever going to use it. And then lastly, how often do you use algebra in your daily life, Dad? Not very often. Then why do I have to learn it? So you can help your son with his homework. We've been doing it for 119 years. Let's not think about it. Let's just keep doing the same thing. We often lament the fact that we go to a cocktail party and people say, I can barely balance my checkbook. But they'll never say, well, I hated English. I hated English. But it's because it's as if we're English teachers only teaching Shakespeare and grammar. Hey, Shakespeare is beautiful. Grammar is a technical skill that everybody needs to know. But in high school, there is a contemporary literature that's part of the curriculum. And what I'm interested in, what is the equivalent, mathematically, of that contemporary literature? Now, I think we can all think of topics that perhaps are part of that equivalent of contemporary literature for mathematics. But there's no room on the curriculum table. If you think of this as the curriculum table, we're constantly trying to shove one more thing up there, but it just falls right back off. So what I'd like us all to do right now is think about a topic that you teach. Everybody, please think about a topic that you teach, that you wish you could drop. It might be good mathematics, but you say, you know, I'd be willing to drop that to make room for a more relevant topic. So everybody please think of that topic. And after you've thought of that topic, then share it with the person next to you. I'm sorry to interrupt. It sounds like we could go on for quite some time, but I'd like to hear what some of these topics are. Yes.
Factoring trinomials.
Yes. Louder. Distance formula. Somebody else. Yes.
Direct variation.
Yes. Somebody else. Yes. Completing the square. Next. Trig identities. Yes. Conic sections. Now the challenge here is the following. For every topic that's been shouted out, there probably is somebody else in the room that says, hey, that's my favorite topic. Right? That is the issue. Because none of this is bad mathematics. That's not the point. It's not bad mathematics. There's just not enough room on the table. So what I'd like you to do for a moment is imagine that we're going to wipe the table clean and there's nothing on the table. And now let's have the discussion about what's the first most important thing to put on the table, and then the second most important thing, and the third thing on the table, and then maybe conic sections makes it on, and maybe it doesn't. I think we all feel that if we had a near infinite amount of time, that eventually we study conic sections or the distance formula, what all the things that you've mentioned. But I'm not sure that the topics that have been mentioned would be things that would be easily argued by a group of us to put on the table first. So now what I'd like to do is move towards examples of what I would think would be a relevant curriculum, what I suggest is a relative curriculum, of things that we might put on the table first. And what I'd like to do is go back to the NCCN standards of 1989 and say perhaps these are the topics that we need to put front and center. If you look at the summary from the Common Core standards, notice at the bottom, statistics and probability. There's always at the bottom, and it's usually the last chapter in the book. Only 10% of the SAT 2, Math Level 1, and Math Level 2 are probability and statistics. So let me suggest some of the topics and examples of things that might go on this curriculum table, front and center. First of all, statistics. I think everybody agrees that people should have more statistics, but no one is willing to take ownership for that statistics. College professors want people to have more statistics. We want people to have more statistics, but nobody takes ownership, and I would suggest we need to take ownership for that. In statistics, I think the #1 topic that is missing is learning about standard deviation. So this is about diabetes. How many of you know someone personally that has diabetes, taught someone this past year that has diabetes, or have diabetes yourself? Raise your hand, right? This is something that affects all of us. So, we have here, there seems to be a lot of buzz about the fact that it's not just A1Cs, that's blood glucose anymore. Rather, it's about the standard deviation to evaluate your success of diabetes management. If you think about it, it's really just common sense. A simple average of your blood glucose over the past 3 months doesn't tell you how far you strayed from the ideal range. You may get an excellent average, but it's nothing but just a middle point. So Dr. Hirsch, a diabetic himself, suggested, just from empirical data, that you should take the standard deviation of your blood glucose times 2, and that should be less than your mean glucose. For example, if a patient's mean glucose is 140 milligrams per deciliter, the target standard deviation should be less than 70. I think this kind of idea could help people with diabetes manage their blood sugar, and it could really help them, but it's not going to help them unless they know what the standard deviation is. And giving them the formula with sigma notation is not going to help them manage their blood glucose. They need to have a visceral understanding of what standard deviation is about. Here's another example. In 2008, the stock market did really poorly. This is 1930 to 2000, and this is market returns. And in 2008, yes, the market was awful. But the question that many people ask is, how unusual was the stock market in 2008? In order to look at that, what we need to do is keep the same timeline on the x-axis, but to look at the standard deviation of monthly returns on the y-axis. And if you do that, then you get some sense of the spread, how unusual was it in 2008? And what we can see is, yeah, it fluctuated a little bit more, but was it really unusual? No, right? Was it really unusual? So I know you can't read all of this. The entire presentation is online. You can take a look at it. I just want to tell you about this project that I do after my students really understand standard deviation. And that is, I give them data that comes from the New England Journal of Medicine, where researchers went around to 5 continents, 43 cities. All these cities had both a KFC and a McDonald's. They purchased fries. They analyzed them in the lab, and the variable that they were interested in was percent of fat that is trans fat. So they had 2 comparative univariate data sets. What I have my students do is analyze these two data sets, and then they see that one has a higher mean, one has a higher median, one has a higher standard deviation, one has a lower standard deviation. Some are skewed, some are not skewed. And what I ask them to do then is to write a paper and write it as if they wanted to submit it to a journal, saying that McDonald's is the healthier fry. But of course, if you're going to submit it to a journal, you can't say McDonald's is the healthier fry. You have to say things like, the data clearly shows that McDonald's is the healthier fry. And when they're done, then they have to write one that says KFC is the healthier fry. And so here's examples of student work in which, look, this is a box and whisker plot. You can see they're leading you right down the path that says KFC is the healthier fry. It has lower percent trans fat. And they say here, and they said in their paper, that here's the maximum of KFC, and 25%, even 25% of McDonald's is above the maximum of KFC. For heaven's sake, you'd never want to buy McDonald's. KFC is clearly the healthier fry. Then what they did, now this is KFC and this is McDonald's. Now they focused on spread, and they said this is the mean plus 1 standard deviation minus, saying down here, and they're saying, look at this huge spread of KFC, and look at this tiny spread of McDonald's. McDonald's is the consistent fry. don't risk your health by sometimes, right? I call this the spinning the data project, and my students come back and tell me the next day, the next week, and even at reunions, wow, that one project changed forever the way that I consume information from the media. Time out, you might be saying, for whom is this curriculum intended, right? Perhaps you're starting to drink the Kool-Aid, but I got to go back to school, and I'm teaching Algebra 2 next year, and I can't just choose a different textbook. What am I going to do? So I would suggest that at bare minimum, when students leave Algebra 2, and we're scratching our heads and saying, you know, this kid's never going to take calculus, right? And you know, I don't think this kid should really be taking pre-calculus. What we often do is just whatever and pass them on. At least at that moment, we have to say, they're usually done taking standardized tests. Why can't we give them a curriculum that's designed for the world that they live in? And that would include statistics. I believe that we could start pulling this backwards and trying to capture more of this 92%. Remember, trying to push this 8.2% is not a very effective mathematical model. Trying to capture part of the 92% seems to make a lot more sense to me. I think that the standard deviation is the gateway to the normal distribution, and the normal distribution is the gateway to the rest of statistics. So I'd like to talk for a moment. I think that every high school student should understand about the normal distribution. Very often when we collect univariate data, the distribution is normally distributed. Not always. Plenty of examples where it's not, but very often it is. And if you only when you understand the normal distribution can you understand so much of more complicated statistics. So I have my students at the very beginning of the chapter watch a video of a 100-meter dash. And it's very clear in this video exactly when the start is and exactly when the finish is. And they all have a stopwatch that has accuracy to the nearest thousandths of a second. And we watch this video 10 times, and they collect for themselves a little data set that says how long was it from start to finish. And what happens is that this is student A, dot plot, student B, dot plot, and so forth. And there's a hint that each one is starting to form a bell-shaped, maybe not normally distributed, but a bell-shaped distribution. And if we put them all together in one group, then it seems, wow, it seems bell-shaped. Now you can't conclude it's normally distributed, so I have them calculate what percent lies within 1 standard deviation of the mean, 2, and 3, and see if it conforms to the empirical rule. And if it does, then they can conclude that it's normally distributed. And it's like magic. Of course, it always conforms to the empirical rule. Later on in the chapter, I have students deal with this problem, which deals with blood alcohol content. In most states, if you're over 21, the blood alcohol content, the minimum that will get you arrested for driving under the influence is 0.08% blood alcohol content. Now, I found that the most commonly used breathalyzer in the United States is the Alcoholic Elite Digital Model 1000 by Breathalyzer, and it has a standard deviation of 0.0037. Now, they're trying to say the relative accuracy or inaccuracy of this device. So what I have students do is consider it's part of a larger problem, but the core of the problem is the following. Somebody gets pulled over and blows a blood alcohol content of exactly 0.080. Darn, I just got caught. Now the question is, if the data would be normally distributed if you blow into it over and over again, given the standard deviation of 0.0037, what's the probability that your blood alcohol content was exactly 0.079, but you were measured at 0.080 or higher? And the answer is about 40%, right? If you don't understand this normal distribution, sitting on a jury, you're making nonsense decisions perhaps, uninformed decisions at least. And remember this 0.0037, they're bragging about how accurate it is. Once you take it out of the box and start using it, that standard deviation is going to grow. It's probably a lot higher percentage that you weren't actually not guilty. that you're actually guilty, rather. All right? Simulation and probability. A small percent, fortunately some percent, but only a small percent of our curriculum is probability. But I think we've painted ourselves into a corner, the approach that we take. And the approach that we take is teaching probability with theory. The challenge with teaching probability with theory is that simple probability theory allows us to do only trivial problems like socks in a drawer, and no one cares about socks in a drawer. The probability theory becomes very complicated after that very quickly. It puts the fear of God into lots of us as we approach teaching it each year. So what I suggest that we do is study probability through simulation. The advantage about teaching probability through simulation is that you can start studying contexts that are interesting, captivating right from the very beginning. And more importantly, it mimics what researchers and people in industry, the way they deal with probability. If you're studying the traffic movement through a large city, you clearly would not use probability theory. You would use simulation. And people in research and in industry solve these complex problems not with probability theory, but with simulation. I'm not saying you should never do it. Why don't we start there? Why don't we give them a good idea of what chance is all about? So here's a problem. There's a company with 400 employees, 320 are men, 80 are women, and they have to fire 10 people. Economic bad times. The pink slips come out, and it turns out that 5 are men and 5 are women. And the women say, this isn't fair. Like, what's the chance that if they did, because, the company claims that they're firing people randomly. The company claims they're firing people randomly. The women say, this isn't fair. Well, what's the probability that if there were this distribution of men and women and they fired them randomly, that you would fire 5 women and 5 men? So if we look at a simulation, so here I have 400 employees. I've broken this because there's not enough room to list all 400. And here's a random number associated with each employee. And then there are 320 M's for men and 80 W's for women in this column. And if I randomize this, then we can see for this particular firing, 1 woman was fired. For this one, 3 women were fired. Now 4 women were fired. 0 women were fired. 2 women were fired. I have my students simply do this over and over again and get the relative frequency distribution. And as the number of trials increases, the relative frequency distribution approaches the probability distribution, and then they can make a very informed, and then they have a lot of information to explain how likely it is. So, then what I say is, imagine you were hired as an expert witness by the women who are bringing the class action suit. What statistic would you report? Now imagine that you're hired by the company as an expert witness. What statistic would you report? And finally, if you're on the jury, after hearing these 2 arguments, both of which you've given yourself, would you find for the women or would you find for the company? Next topic, recursion. If you see a list of numbers like 10, 12, 14, 16, your brains see it recursively. That's one important reason. We have lists of numbers all around us, and our brains see it recursively. So let's not fight it. Let's use the notation the way our brains think. There's a second important reason why I think that we should study recursion, and that is there are so many applications in which, particularly involving money, if you had a purely geometric or purely arithmetic context, you could use the explicit form. But when you combine the 2, recursion is really simple and the explicit form is incredibly complicated. And here's an example. In 2010, the average American household had $15,788 in credit card debt. And they were paying an average annual percentage rate of 14.8%. Now, if we can't get our own finances under control, how are we going to get the U.S. national debt under control? So what I have my students do is find out if you have that much credit card debt and you're paying that much interest rate and you're going to make the minimum payment, how long would it take you to pay off your credit card debt? Now, I clearly can't take the time to show you how this Excel spreadsheet is created, but I want to mention two things about it. Number one, the main idea is this cell right here, and it's the recursive cell, and it's quite simple. The balance this month is the balance from the previous month times 1 plus the rate. That's the geometric part. Minus the payment, that's the arithmetic part. And recursively, that's very simple. Right? So what we do is we bring it down and we say in around 37 years, making the minimum payment without any new debt, you would be debt-free. The second thing I want to say is that Excel is the world's number processor. There are word processors and there's number processors. When students walk out of the last math class, they will no longer use GeoGebra or the graphics calculator or Sketchpad or Fluid Math. They're not going to use any of these ever again, but they will use Excel if they work in industry, do any kind of research, anything. So we might as well, I think it's so important that we prepare them for one of the most important technical skills that they could possibly do in a quantitative context. What we do after we've done it in Excel is we put it into a repayment calculator, we put in the information, and it gives us exactly the same answer, 37 years, right? It's just not voodoo here. They know, they're just showing that they know exactly where these numbers come from. The next area, second to last area, is large and small numbers. The curriculum of 1892 had no large and small numbers in it. And ours, fortunately, has some, but not very many. But the world around us is full of large and small numbers, from the size of the national debt to the probability that you're going to win the lottery. Gene Lowe's at UCal has asked many, many people this question. If this is a number line where this is 0 and this is 1 billion, B billion, then where does 1 million go? Most people put it about here. If the general population thinks that 1 million is a third of 1 billion, then we're going to hell in a handcart. We're not going to be able to get our national debt under control. So here's an example of large numbers and small numbers. So this is a graph of the Dow Jones Industrial Average from 1970 to 2010. This is when I was a junior and senior in high school, and the stock market wasn't doing particularly good, particularly poorly. It was pretty flat, and I was about to go to college, and my parents weren't particularly worried. They'd been saving, but the stock market was doing okay. This is when our son Bjorn was a junior and senior in high school, and Lisa and I were wondering, how in the heck are we going to pay for college? But anyway, this is comparing when I was a junior and senior in high school and our son was a junior and senior in high school. As it turns out, 1973 and 1974 was the 7th worst stock market crash in the history of the United States. 693 days of decline, 45% loss of equity in the market. Right there. And why can't we see it? We can't see it because we're using a linear scale here. When you use a linear scale, and one of the variables spans, let's say, more than 2 orders of magnitude, you can't see any fluctuation at the lower value. Right? It went down, let's say, from 100 to 50, right? Losing half of the value. Well, it did about the same thing here, but we just can't see it. So if you go and look at this at yahoo.finance.com, it won't come up with a linear scale. By default, of course, it will come up as a logarithmic scale. And when you bring it up as a logarithmic scale, then this height drop and this height drop are about the same, showing that in both cases there was about a 45% loss in the market. We are all looking at making decisions about our retirement, looking at pictures like this, and most of us don't notice. And for years and years, I didn't notice that these were, when it was a logarithmic scale and when it was a linear scale. Next example. This is from Gapminder. So in this picture, let's see, how do I go to full screen? Great. So this is Gapminder. How many of you know Gapminder? Okay. So this is a picture where this is income per person down here internationally, and this is life expectancy. Every circle represents a country. The diameter of the circle is proportional to the population of the country. And this is a snapshot for 2009. In blue is Africa, yellow is America, and so forth geographically. Now what we can do is we can see what happens from starting, this is a picture in 1800, and I've highlighted 3 countries, the United States, China, and India. So here we are in 1800, and not much is happening in the early 1800s, and all of a sudden you can see a little bit movement here of the United States. But it's still pretty flat until all of a sudden, in around 1830, 1840, the United States is starting to move up in income per person. Nothing's happening with China. India is still dead over here, and but there's some movement over here with the United States. Now we're in 1860. China is doing some movement down here, but nothing significant. The United States is moving up in income per person, but not in life expectancy. But in 1886, approximately, the United States starts moving up. India and China are still wallowing down here in poor land, and the United States is now moving up both in income per person and in life expectancy. Until now it's 1924, 1926. Look now, focus what China does. China takes a movement up to the left. What's going on there? Now it's 1950, and China then heads back up. The United States is still going up there, and they're way, way behind. It's now 1967. They're moving up in life expectancy, but they're not moving up in income per person. All of a sudden, in around 1980, they take a right-hand turn and heading towards the United States. Now it's 1993, year 2000. Now we're almost at present. So what's happened? So there's so many things that we can see from this. The one thing that we can see, sort of rate of change moving in this direction by the relative distance between disks. We can see that the direction that they're going, we can see clearly that now China and India are aimed at the United States and moving towards the United States. And you can then easily project when are they going to catch up, because the United States is slowing down. But one of the things that's interesting here is what was happening in there. What was happening in there? That was from 1935, 1950, something like that. The Chinese Revolution. During the Chinese Revolution, the income per person was going down, right? Now, why did I show this example?
The logarithmic scale.
This is a logarithmic scale down here. Of course you'd have to use a logarithmic scale, because the values of the variable of income per person over all the countries in the world clearly spans more than 2 orders of magnitude. And if Gapminder didn't, by default, show a logarithmic scale, then this area right here for the Chinese Revolution, focus on that area right in there, please, would look like this. Can't see any fluctuations in the lower value, right? Looks completely different. We have this dilemma when we're trying to show information where the values of the variables have a large range. Either you use a logarithmic scale and people don't know it's a logarithmic scale, or they use a linear scale and you can't see fluctuations in the lower values. And last example, or set of examples, linear to exponential. And here's what I mean about that. Some of you might be relieved that I am going to add some functions to the curriculum table, and here I go. I said I would turn the NCTAM standards of 1989 up on its head and the Common Core standards, and that's what I'm doing. But now, let's put them at the bottom. So it makes sense if we're going to study the toolkit functions that we start with linear functions and their transformations. Makes sense. Where do we go from there? Y equals x to the 2 or y equals 2 to the x? Well, I understand that we would want to spend some time here because there's one really important application. When you drop something, the height over time is quadratic. And when its path in horizontal and vertical is also quadratic. And then the applications seem to slow down quite a bit. There are applications. Occasionally somebody comes running across 10 lane. I found one. An application, for polynomials. Whereas over here, for exponential functions, there are a huge number of applications, unending number of applications. So I think we should emphasize over here and drastically de-emphasize here. My conjecture why we spend so much time with polynomials is that when we get to calculus, it's easy to explain the rules of differentiation and integration with polynomials. How convenient. So let's just spend 4 years prepping for that moment, right? Right? I'm not anti-polynomial, I'm just saying, you know what? The application's over here. If we want to make people quantitatively literate, we better spend a heck of a lot more time over here. And so here's an example. So it turns out that the blood alcohol content for alcohol decays linearly, and for most other drugs, decays exponentially. So if you're taking, this is an arbitrary scale here, but let's do a comparative scale where 8 is the overdose. Critical area, everything over 8. So if you've taken Valium, if you've taken ibuprofen overdosing on any of these cocaine, psychotropic drugs, and you've taken too much, right, then you quickly come down out of the danger zone. But alcohol in your blood forms a toxin as a byproduct of metabolization. And your body says, time out, I can't metabolize anymore because there's too much of this toxin in my system. And so that's why it decreases linearly. Now, so I talk to kids about the following concept. If you binge drink, once you get that alcohol in your system, time is the only thing to get it out. And you're going to be in that toxic zone for a long time. So if you're going to drink, and you're going to drink 6 beers, then you should drink 1 and let it metabolize, another one making a sawtooth, staying below the toxic level, overdose level all the time. So you might want to drink a beer, wait an hour. Drink a beer, wait an hour. Some of you might think about doing that as well. The point here is the phenomena around us are almost always linear and exponential if we're looking for the toolkit functions. And the polynomial functions, there aren't very many. Let's study some of them, but let's move on. Because of time, I'm not going to share this last example. It's about global warming. Let me just say, this is the Keeling curve. Let me just say that if our kids don't understand the quantitative analysis of global warming, then it doesn't make any difference what we teach them, right? And I'll admit, I'm trying to convince them that global warming is a problem. What's important is that they can make their own decision about global warming. And if we really educate them about this, hopefully they're going to get agitated and do something about it. Anyway, I'm going to move on and end by saying the following. I've talked about examples of a relevant curriculum. Let me briefly talk about characteristics of a relevant curriculum. First of all, I think they need to be utilized. I've given many examples I hope are compelling that can be used in a day-to-day context. But let's think about college. Most students go on to college and don't use calculus in college. Okay, math majors, engineers, and hard sciences, yes, they use calculus. But if you're studying most anything else, it might be a requirement to take calculus, but that's all. Basically, are you smart enough to jump over this hurdle and stay in our institution in this track? But then it's not used. What is used if you're going to do any kind of research in any of these fields? Statistics. Secondly, less is more. We need to start giving them captivating problems. 1 through 31 odd and 43 ain't doing it. Perhaps we should just be doing number 43. I think we need to have virtual resources instead of textbooks. This is really important for public schools because you buy a textbook and then you're stuck for 6 or 7 years. So if we make virtual resources, then they can make quicker decisions, like those of us that teach in private schools have the privilege to do. And lastly, I'm a big believer that content should be open content and free, that the NSF should give a priority to funding curriculum development teams that say, we're not going to create this and then publish it to make money. We're going to, yes, we're good writers, give us some money, and then we're going to make it open and free to everybody, so that everybody can say, that's the best curriculum. Let's start using that. And lastly, that it should be designed for the majority. That this curriculum should be less esoteric, understood for or meant for only the select few, like poetry full of esoteric allusions. Or number 4, intended to be relevant only to the initiates of a group, like the esoteric doctrines of Pythagoras. And less exoteric, suitable for or communicated to the general public. We are doing an outstanding job with the top 8% of our students. But there's a vast, lost majority of students who are ready for us to turn our attention to them. They are hungry to learn a curriculum that is designed for them and the world that they live in. They are ready to succeed in a math class, and if they do, they'll sign up to take math class again next year. And they are eager to become quantitatively literate. But they're waiting for us to deliver it to them. And I'm confident that if we deliver this to them, they will respond beyond our wildest imagination. Thank you very much. Glad to take them, or comments, maybe comments too. We don't have to. Anybody? Yes?
Maybe you should share your website.
I have a website called Ahbel.com. I don't sell anything on it, but if you Google my last name, you go to Ahbel.com, and if you look at it's under past presentations, you'll see a link to this Prezi. And and also, I wrote a full year's worth of curriculum that's free and open, designed for students leaving Algebra 2, and a curriculum that has all of these problems and many more, and that content is open and free and for anybody to use. A full year's worth of curriculum. Yes?
Have you attempted to implement this development curriculum, and if so, what's the response of your school?
Have I tried to implement this curriculum, and what's the response of the school? One of the things that I can tell you is that I've spent most of my career teaching kids, focusing on kids who hate mathematics and have done poorly the year before. And if you offer them this type of curriculum, actually often what happens is that they'll go home and start talking at the dinner table about what they studied in school that day. And when you talk to parents at parents' night, the parents look at you and say, what are you doing with these kids? You never talked about math before, and suddenly they're night after night talking about these kinds of issues, because I believe they're eager and hungry to learn this kind of stuff. That's been my reaction.
How do you spell Ahbel.com?
Ahbel.
Ahbel.
Thank you.
Yes. It's not to confuse me with the other Nils Ahbel, who died in 1827, father of group theory. Yes.
Would you please consider making the video that's been recorded tonight available?
I hope to do that. I hope to put it on my website. If it turns out well enough, I would be glad to do that. I hope to, like to make everything that all the content that I create free and available. Thank you.
Thank you.
Send me an email if I don't do it after a while. Yes. Okay, thank you very much, everybody.